if if you all will think back to like algebra 1 when we first introduced function notation, do you remember that being kind of confusing, maybe a little painful back then? They're like, all of a sudden it's not y anymore, it's f of x. What's up with that? And now you're going to put like f of 2 in there, and it's like, why can't you just say y equals and ask me what it is when x equals 2? It was easy. That why you got to make things complicated. And the reason is it's convenient, it's nice notation. It allows you to convey a lot of information in a short amount of space. You two are going to need to stop too, okay? So that's what this is. This is just a way to conveniently convey some information. It's going to look weird to you. It's going to feel a little strange to you until you've done it a couple times, and then you'll be like, oh, I know exactly what this means. The same thing as function notation. So I want to tell you how to pronounce this, and then we're going to translate this in English. You would pronounce this as the limit as x approaches negative infinity of f of x equals infinity. And I'm going to write that down here. I know, isn't that awesome? The limit as x approaches negative infinity of f of x is infinity. That's how we say it. I'm going to translate it, and it's going to make a lot more sense to you. So that's the way we pronounce it. By the way, limit notation is a convention. A convention is just some arbitrary rule or way of doing something that like a whole bunch of people have agreed is the right way to do it. So I need it to be, when we're writing or limit notation, I need it to be in this format. This format has kind of smaller text for the limit and the x approaches negative infinity. These need to be stacked on top of each other. The f of x equals whatever that is needs to be a little bit bigger off to the side. So make sure you're following the same kind of notation. It's not okay to get creative with this and invent your own new type of notation. I mean, it's totally okay to do that, but I won't accept it for full credit on tests and quizzes. Big thing I need you to know is that these two numbers here are the kind of important things, this negative infinity and the infinity. Everything else always looks the same. Let me translate this for you, though, so you know what this means, so it's not so scary. All this is saying is on the left, that's what this part of it means. On the left, and this part of it means it goes up. That's it. So if we're talking about a graph, if I look at a graph, and somebody wrote this about the graph, I'd look at this and say, oh, they're just saying that over on the left, over here, on the left of this graph is going up. Now, can you kind of see how that makes sense? This says x is going to the negative, right? You see how that means on the left? If x is going to a negative, x must be going to the left. So off to the left of the graph. And this is saying y is going towards a positive. Do you see how that means that it's going up? So when x is going negative, we're talking about on the left side of the graph. When y is positive, we're talking about it going up, okay? That's it. That's all it means. And it's a funky way to write it, but you can convey a lot of information. We'll add some other little details into it later on, put some little plus and minus symbols as kind of exponents here. And that just conveys another piece of information. But that's all it is. It's a fancy way of saying what's happening on the left and what's happening on the right of a graph, okay? And what that is called end behavior. And I know you've seen this before. So let's practice with a little end behavior. And while we're writing our end behavior, instead of describing it the way we did last year, we'll describe it using this limit notation. And this will give us an opportunity to practice. You're going to get some great opportunity later on in the period to practice this as well. So we'll just do a couple. Okay. So here's a nice graph. That's kind of looks like a quadratic to me. It's trying to be anyways. So if I ask you to describe end behavior, what would you have written down last year? You would have an interval notation. Okay, that's fine. So when we do end behavior, we do have to give both what's going on the left and the right. So we'll do that separately. So over here, what's going on the left? On the left, it goes up, right? On the left, it goes up. And while we're at it, let's write it down in English. On the right, it goes up. So you can look at it and see what's going on, whether it goes up or whether it goes down. In this case, we're going up on the left and the right. There is a third option other than up and down. It's possible for the graph to kind of level off at a particular value. That would be if you have a horizontal axis. So we'll do an example of that in just a moment. Let's translate this. So in limit notation, like I was saying before, there's sort of a format that's always used, and then you just have to fill in a couple values. So go ahead and write this out for me. Leave the infinities and the negative infinities out for right now, and just write the format down, and then we'll come in and we'll fill in the details here. All right. So we got two important concepts for our left end behavior. We got the idea of left and up. When we're talking left, are we talking about X values or Y values if we're going to the left? Left is X values, right? Left and right are X values. And left, are those positive or negative X values? Negative. So X is going to go to negative infinity. If we're talking left, then that must be the X values going negative. We talk up and down, now we're talking about Y values, right? So that's our f of X. And this says up. So if we're going up, are we going positive or negative? Positive. There we go. See if you can fill in the other half of our end behavior here on your own. I believe in you guys. I think you got this. And then we'll do another example. How'd you do? We got it? Awesome. All right, here we go. Next one. This one's going to have a horizontal asymptote. This is actually going to be an exponential function, but it's had some transformations done to it. So it's been flipped over, it's been shifted, but it looks like something like that. And our asymptote is going to be y equals 2. And this time, I think you guys are getting pretty good at this pretty quickly. So why don't we see if we can go straight to the limit notation this time? If you're feeling confident, give it a try on your own. This one's a little bit different because of that asymptote. One of those infinities from the previous one is going to be a number this time. That's my big hint to you. Like an actual number, not a conceptual number like infinity. So let's start here. We're going to the left. That's x heading towards negative infinity, correct? Now this time, as we move to the left, the graph is not moving up or down. It's kind of leveling out at a particular value, and that particular value is 2. So 2 goes here. So the y is headed towards 2. How many people were able to get that? Hey, nice. Look at you. All right. And then on the right-hand side, so this would be positive because we're going to the right. X is going to the right. Now this time it is going down, 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 down forever and ever to negative infinity. If you got that, then you are good to go with this. If not, we'll have some time for me to help you out with some questions and examples later on. All right, let's move on. There's 2 big concepts in 1.3. That was kind of background information. The next thing we're going to talk about are piecewise defined functions. Piecewise defined functions. These are the chimera of functions. You guys know what a chimera is? It's a mythical creature. Don't know about that. Did it cause a bunch of animal parts to be stitched together into some crazy grotesque thing? Yeah, okay. So a chimera in Greek mythology, I think it has the head of a lion, the wings of a body of a griffin, maybe like wings of an eagle. Does it? Okay. Sometimes it has a snake for a tail. Yeah, it's a bunch of animal parts stitched together into something, and that's what a piecewise defined function is. It's a function made up of a bunch of other functions. So let me give you an example of what an equation would look like, or a definition, I should say, for these. So instead of f of x equals, instead of like one expression after that equal sign, you're going to have multiple ones. And we use a sideways mustache here to hold them all together. Hey, folks, please, I've asked a couple times, can we limit the chit chat? Thank you. There are going to be 3 parts to this particular function. There can be hundreds. A lot of the ones that you'll do in your assignment are going to be just 2. So the first thing that we're going to put together to make this function is the equation y equals x squared. Can you picture what that looks like? Parabola, except we're not going to use the whole thing. We're only going to use a part of it. We're going to use the part where x is, bless you, less than 1. That's if in the middle there. The second function that we're going to use a piece of is the function y equals 1. Can you picture the graph of y equals 1? Horizontal line crosses the y-axis at 1. We're not going to use the whole thing. We're going to only use a little piece of it. We'll use the piece between 1 and 2. We'll include the 1, but not the 2 in that. And the third piece of our function is going to be the function y equals x plus 2. And just like the others, we won't use the entire function or the entire graph of x plus 2. We'll just use the portion of it where x is greater than or equal to 2. So the way that I'm going to do this for our notes is I'm going to draw 2 copies of this graph. We'll kind of do like a rough sketch and then a final graph. But when you do it in the homework, most of you won't do 2 copies. You'll just do it at your rough graph in pencil, and then you'll erase off the parts you don't want to make your final, okay? But for our notes, I think it's a good idea to draw 2 versions of it. So I'm going to eventually have 2 xy axes side by side here. The one on the left will be our rough draft, and then eventually we'll come back and make our final graph. Again, usually when you're doing these in your assignments, you'll just do it once, but I think it's a good idea to show our steps and our thought process in the notes. And I'm going to color code mine, but if you don't have color stuff, that's okay. We'll draw some labels on it and it'll be fine. All right, so here's what we're going to do. I'm going to graph all 3 of these. I'm going to graph the entire graph for all 3 of them, and I'm going to do it in dashed lines or very lightly. And I will color code mine. So I'm going to do my x squared in red. as former Algebra 2 students, I'm assuming that you can all draw a reasonably accurate graph of y equals x squared without thinking too hard about it. I did say dash line, didn't I? And I didn't do it. And if you don't have colors, that's okay. We'll just label here y equals x squared. Hey, what's up? All right, we're not going to keep this whole thing though. We're only going to keep the portion where x is less than 1. Now, this is, anybody ever flipped x's and y's when you're dealing with graphs, especially when it comes to like increasing and decreasing and all that stuff? It's easy to do, and it's really easy to do here. So I'm actually going to block off the portion of the graph I'm not interested. This says x is less than or equal to 1. So I'm just looking at the portion of my graph where x coordinates are less than or equal to 1. We just want that. Let's go ahead and darken in that part of our parabola here. That's the part we're going to keep. We're going to chop the rest off and throw it away. Tell me about this point here, 1, 1. Should that be an open dot or a closed dot? Open because less than, right? Not less than or equal to. Agreed. All right, there's the first part of our function. We're going to stitch that together with a couple other pieces. So let's go ahead and do y equals 1. So draw that, again, dashed line. Same graph. And we'll go back and darken in the portion of that we're interested in. And we only want a tiny little bit of this, just between 1 and 2. So I'll darken in that little portion there between 1 and 2. So it does kind of overlap with this one at the end. What's going to happen at the 1? This says less than or equal to, right? So this one is actually going to include that. That means that it's going to actually fill in that open dot since it's at the same spot. And then at 2, looks like we'll have an open dot at 2 here. So far, so good. And let's label that was the equation y equals 1. And then our final piece is going to be the function y equals x plus 2. So that has a slope of 1, a y-intercept at 2. So draw that in, again, dashed. And we'll come back in and darken the piece that we're interested in. So we're going to keep this graph only where x is greater than or equal to 2. And be careful because it's really easy to read that and think y greater than or equal to 2. Like, make sure we're looking at just the portion of the graph where x is greater than or equal to 2, which would be this part up here. Greater than or equal to, so we want a solid dot here. And I'm going to label y equals x plus 2 here. So if I were doing this on assignment, I would do all that stuff, then I'd just come back and erase my dash lines and we'd be good to go. Since this is our notes, let's draw our final version. So I'm just going to sketch everything all in one color. Let's see here. We got sort of a parabola-y thing here, goes up. And then we come up to here, and that's included. And we go over, that's included. We got a piece up here. And that's it. So you can imagine you can make all kinds of funky shapes with these graphs. Yes. This point right here. Yeah, so if you had just drawn this without that dot there, that'd be fine. So do we feel okay about graphing these things? It's kind of like 3 problems for the price of 1. Hey. So I want you to feel good about graphing them and then also about evaluating them. So I'm going to ask you a couple more questions before we go on to the final piece of our work today. I'd like you to pretend that you cannot see the graph. Does anybody have any questions about the graph before we move on? Yes. So there is a way to do that. I'm going to defer that for now. You can do a Google search on how to graph piecewise defined functions. You use division. I'll show you in a minute if you like. Okay. I want to move us along. I'm going to tell you that when you see stuff in your assignments, these are going to be the types of functions that you should be able to graph without a calculator. Now, if you get something in here that's like lnx and you can't remember what lnx looks like, go ahead and graph lnx in your calculator and then add it to your function and just keep the piece that you need. Okay. There is a way to do it though. I'll show you in a minute. Ask me again once we've when we get started checking assignments. Okay. I also want you to be able to evaluate. So imagine you can't see the graph. This is actually pretty easy to do if you can see the graph. Imagine you can't see the graph and I ask you to evaluate f of -4. Now you're comfortable with function notation. You know that when I say f of -4, that means take -4 and plug it in for x, right? The trouble with this is we've got lots of different x's we can plug it into. So are we going to plug it into this one or this one or this one? Or all 3 of them? All 3 is not the right answer, but it's my favorite wrong answer. The key is over here. Okay, this tells us where to graph. It also tells us where to evaluate. These are called the subdomains over here. Which of these subdomains does -4 fall in, the first or the second or the third? Only it falls into the first, right? So that means we want to plug it into the first function. Okay, so you have to look at the number, match it up with one of these subdomains, and then that tells you which one to plug it into. So we're going to plug it into x squared. So we'll put -4 in there and we'll get 16. So show me you guys are feeling okay about this by evaluating the following for me. Could you please find f of 1.5 and f of 1 and f of 7. And if we're feeling good about that, we'll call it a day. You don't have to show me work if you don't want to. Well, let's do f of 2 also. Just for fun. So I'm putting answers up here. If you're still working, don't look up here. Spoilers are on the board. So once you finish that up, check your answers, see how you're feeling, ask some questions. I have one more question here before we'll go on. This last question I'm going to ask is going to be one of those like last question on the test. You guys are going to find that most tests, the last question is going to be the type of thing where I ask you to put together multiple concepts, make some connections, and it will almost always be something that we have not gone over specifically in class. Why do I do that? Because I feel like in order to earn an A in this class, you need to be able to make those types of connections on your own. So the question will never be enough to bring you from like an A to a B, but might bring you from an A to an A minus. Okay. So but I'll give you lots of those types of questions as we're going along. Is that a phone underneath your? I appreciate that you're honest about it, but thanks for sticking it in your bag. Okay. Any questions here before I give you my questions? Yes. Yeah, so this is a weird function, isn't it, right? This function is y equals 1. So no matter what, like if I gave you a function, let's forget about f of x. Let's say I give you a function g of x equals 3, okay? And I ask you, what is g of 10? What's your answer? 3. And I ask you, what's g of 1,000? It's 3. It doesn't matter. You're always going to get 3. So the reason that 1.5 is giving us 1 is that 1.5 falls between 1 and 2. So we're definitely in this subdomain. Anything in this subdomain is going to give me an output of 1. We just put 1 in. And you don't have to show me work on these if you're doing them. If you can do them in your head, that's fine. Yep, thanks for that question. Any others before I give you my big last question on the test? A style in the style of a last question on the test. We'll talk about that when we get close to the test. Okay. I told you I'd be transparent. I will stand in front of you and I will tell you exactly what's on the test question by question before. Oh, when is it? 3 weeks, maybe something like that. You'll be fine. You'll be fine. Okay. Hey, here we go. Don't miss this. Okay. These are piecewise defined functions, correct? What if I ask you to evaluate f of some number, and this number happens to be in more than one of these subdomains? And that'd be the answer I'd be looking for. So if I asked you, so if I gave you something like this and I asked you to say find f of 10 and 10 was in more than one of these subdomains, you could give me if I asked you to evaluate it, you would give me the 2. What I'm trying to get at right now is to see if you recognize that if it is in more than one of these, then this is no longer a function. Because what's the definition of a function? For every input, you have only one output. So if it's in more than one of these, then you could potentially have 2 outputs for that particular input, and it's not a function anymore. Now you could have a piecewise defined relation that could give you 2 different outputs. But what I was hoping is that you could make that connection that if it's in more than one of these, I'm going to get 2 different outputs, and then it's not a function anymore. Okay. All right. Last thing for today. So we're going to do a little self-study. I know you guys love just sitting here and listening to me talk and copy stuff down, but this is going to be way better. Trust me. I'm going to help you out with this. We're going to do the first one together. This is going to go right in your notes. Okay. And this is also from 1.3. We are going to talk about our 12 parent functions, and you're going to make yourself a little guide today. You've seen most of these before. We may be adding on 1 or 2 that you're not familiar with, but you messed around with this last year in Algebra 2. You were doing lots of transformations on these things and all that stuff. If you have your books with you, you can go ahead and open up to page 106. It starts on page 106. This is going to take several pages. But the part that I'm going to go over with you is only going to take you like the top quarter or third of the page. You're going to do it in class right now. Okay. And then if you don't finish it in class, then yeah, it'll become part of your assignment. Okay. So we're going to go through this. This is pretty quick. We're going to do this 12 times. I'm going to do the first one with you. So if you look on page 106, you're going to see a series over the next few pages. You'll see a series of 12 graphs, and they give you the names of the 12 basic functions. I call them the parent functions. The first one, they name the identity function. I'm not a huge fan of that name. What other name have you heard for this type of function? It's a linear function, isn't it? Why do they call it the identity function? This one's even worse. Squaring function? Are you serious? I'm not going to call it that. What have you heard it called more often than that? This is a quadratic, and this is a linear. Now, if you want to call it identity and squaring function, that's fine. I'm going with linear. So here we go, linear. We're going to do this quick. I'm going to show you just how fast this is. So you're going to write down linear. You're going to write down the equation for it, which is y equals x. You're going to make yourself a little graph. And then off to the side, we're just going to analyze it. And there's a list of things I'd like you to do to analyze. I'll put those up on the board here in a minute, but I'll walk you through this first one. This is going to take us a matter of just a couple of minutes. All right, I'm pausing here for you guys to get that drawn, and then we are going to launch right into our analysis. What did I do with my sheet? All right, here we go. Off to the side is our analysis. We're going to start off with intercepts. In this class, intercepts get our points, and so they get x, y coordinates. In fact, you don't even have to tell me if it's an x-intercept or a y-intercept, because I'll know where based on where the 0 is. Now, this happens to be both an x and a y-intercept, right? So just write 0, 0. All right, we're done there. Next up, domain. The domain of this function. All real numbers, we're going to write it in interval notation because me and Mr. Height's making you do that for chapter 1. And the range. Same thing. Next up, we got increasing, decreasing. Is this decreasing anywhere? Nope, it is increasing over the interval. Well, it's increasing everywhere. So negative infinity to infinity. Any symmetry? Yep, it's symmetric about the origin, which makes it what type of special function? Other one. Odd. Symmetric about the origin makes it an odd function. If you get a graph that has no symmetry, just write no symmetry. Is it continuous? Yep, so we'll write continuous. If you get a graph that's not continuous, just write not continuous. Is it bounded? Bounded above, bounded below, bounded, unbounded? Unbounded. Any local extrema? Local extrema, those would be local maxes and local mins. Nope. No local extrema. If we did have local extrema, we just list them as points. Local extrema are points given x and a y coordinate. Hey guys, stop please. We're almost done. Any asymptotes? No asymptotes. Asymptotes, of course, you're going to give an equation for x equals y equals. And one last thing, end behavior. No, you don't have to do anything. Yes, it will help you. You should get this done. Like whether you get it finished in class today or you, but you'll get it done. You got lots of time, 25 minutes. This, so far, we've only been on this for like a minute and a half. Yeah. And behavior, we're just gonna write it out. I'm gonna write out my format first. Let's see here. So on the left, that would be negative infinity for the x. It's going down. That's negative infinity. And on the right, that would be positive infinity for x. It's going up. That's positive infinity. And we're done with that one. And we move on to the next. Okay. So I'll have you work with somebody. I'll encourage you to work with somebody. You're free to work by yourself if you like. If you do work with somebody, I'm okay if you divide and conquer. But you should have all these in your notes at the end. So if you want to split it, you do this half, you do this half, and then send each other pictures of each other's notes or something like that to try and make it go quicker. I'm okay, however you want to do it, but you want to be able to think through all of these. There are a few things that you do not have to worry about. So I'll put this list up here. At the bottom, it says for sine, cosine, and the greatest integer function, you do not have to worry about increasing, decreasing, or end behavior. They don't really apply to those, or we don't know how to do them yet. It's down at the bottom of the screen there. And I'll put this back up in just a moment. I do need to show you one last thing. You guys are going to thank me for this.